Welcome to the second lecture on category theory. In this lecture, we are going to be looking at the concept of a functor between categories. In mathematics, when one introduces a certain mathematical structure, that's the data of one or maybe several sets and some operations and relations defined on such data, usually there is a natural notion of a morphism between structures, and the same applies for categories, and it's called a functor. So let's consider two categories, C and D. In category theory, it's useful to have visual representations of the ideas we talk about. And because of that, let me make a little drawing for each of these categories just to remind ourselves what a category is. It consists of objects and morphisms between them. And keep in mind that there could be several morphisms between objects in either direction. And we also have possibly several arrows for each object that loops into the object. But there is one special one called the identity morphism, right? So these are the ones that I'm drawing now, but there could be other looping arrows as well. Just the fact that I'm drawing single arrows doesn't mean that there's only one. And the category D will have similar structure. So there are objects and morphisms, and of course, what distinguishes a category from a graph is that we can compose these morphisms, and moreover, the information of how to compose the morphisms is to be given together with the category. So if these pieces of information are the structure of a category, then it's natural that a structure preserving mapping between them must map objects to objects, and it must map morphisms to morphisms. So there are two types of mappings. One for objects and the other for morphisms. And then it's also natural that the domain and the codomain of the morphisms must be preserved, as well as the composition and the identity morphisms. So if we recall that the way we formalized what constitutes a category was in terms of a system C0, so this will be for the category C, C0, C1, the domain map, but now, because we will have two different categories, we might want to put subscripts to these maps to indicate that they are for the category C. So we think of the category C as a system of the collection of objects, the collection of morphisms, the domain map for morphisms that maps morphisms to its domain, the codomain map, the map that chooses identity morphisms for every object, and the composition map. And D is a similar data, right? So I'm going to replace all of these C's with D's. Then a functor between the categories, so we will call the functor F. A functor F needs to, as we said, needs to map objects to objects. So that was our yellow arrow. So it will have a function that maps from C0 to D0. And it must map morphisms to morphisms. So there will be another function, F1. The rest of the data themselves are functions, and the idea that the functor must preserve the structure of a category will result in preservation of these functions by these two maps. So let's make this explicit, what this means. It's very similar to how you define an operation preserving function in algebra. So what I'm going to write now will not be anything strange at all. So let's begin with the domain map. So if I have an object X, the domain map applies to morphism. So if I have a morphism F, and I consider its domain in C, and then I map that by the functor, which means applying the F0 function, then this should be the same as first mapping F by the functor, but then it's applying the F1 map, right? And then taking the domain of that in the D category. So this is very similar to preservation of a unary operation when you have a function, a structure preserving function between algebraic structures. And similar equalities will be written out for the other pieces of structure of a category. So we have, in a similar way, we have exactly the same thing for the codomain function. So I'm just going to copy this and replace D with C. And we also have the same for the function that chooses identity morphism for every object. There will be slight difference in that equality compared to the first two. So if I apply the function E applies to objects. So when I replace this D with E, I also need to replace my F with X. We usually use small letters for representing morphisms and capital letters for representing objects. So I'm going to call this X. So if I take an object X and I apply to it the E function, which turns this object into the identity morphism of the object X, and then I map that morphism by, this time it will be F1, right? Then that should be the same as first mapping the object by F0, and then considering the identity morphism at that object. And finally, the last equality that remains to be written out here is preservation of composition. So if I apply the F1 map to G composed with F, that must be the same. Okay, maybe I should be a bit more precise. So this is composition in the category C. Then I'm claiming, I'm requiring that to be the same as F1 applied to G composed in the category D with F1 applied to F. Now there is a little potential problem with this equality, because remember, composition is only defined for certain pairs of arrows, the ones that have a matching codomain and domain for the two morphisms. So if I start with the matching situation here, in other words, let me write this out in a diagram. So if I start with a situation where F goes from X to Y and G goes from Y to Z, right? How do I know that on the other side, we will still have a matching situation so that this composite will actually be defined? Would anyone like to answer that? So how do I know that when I apply F1 to F and F1 to G, these two arrows will still match here? So in other words, the codomain of that arrow will be the same as the domain of the other one. Yes, please go ahead, Ephraim.
I think because the diagram has to commute.
Could you please speak louder? I can't hear you.
Yeah, I think the diagram has to commute. The first one. So for it to commute, we should have this map that.
I still cannot hear you. Would you perhaps like to write out your answer in the chat, because it's not possible to hear you. It's very, very quiet. Anyone else would like to speak out the answer if the microphone works? Emmanuel, yes? Emmanuel, I'm sorry, I cannot hear you either. Okay, so we've got in the chat, I think the diagram has to commute. Well, first of all, we didn't discuss what it means for a diagram to commute yet. And secondly, I don't see what commutativity of the diagram has to do with my question. So let me repeat the question. We want to require that F1 preserves composition. And so this would be the natural equality for that. But the slight issue with this equality is that, so we might start with two arrows that are composable, so that fit into a diagram like this. But then on the other side, if I map these arrows, how do I know that the mapped arrows are still composable? If I don't know that, then this composite wouldn't be defined. Yes, Mick? I'm not sure if you're speaking or not, but you're silent. Let me check whether maybe sound problems on my side, because I can't hear you still. Okay, so you'll have a mic issue. Okay.
May I say something?
Yes, please, Gregor.
Okay. So I think it's due to how we defined the F0 map on the left-hand side. There we write that that the codomain of F1 of F must be equal to yeah, the I'm referring to the second one and the first one. Yeah. So there we say that they have to match to avoid that issue.
Wonderful. Yes, I completely agree with you. I hope everybody else also understood that. So it is with conditions 1 and 2 that we are forcing, in a situation like this, for the codomain of F1 of F to match with the domain of F1 of G. Now, you did mention one word. You said it has to do with how F0 is defined, but keep in mind that this is not necessarily the definition of F0, it's just a property of F0. However, because every object will be a codomain of something, specifically its identity map, we could actually think of this also as the definition of F0. So, in other words, if F1 has been defined, then F0 is forced to be defined in a certain way, just because these objects, codomains of morphisms, include all of them, since every object is a codomain of a morphism, specifically, at least the identity morphism is a codomain of that. So remember, identity morphism is the E of X. All right, so the problem is solved here. There is no issue with compatibility on the other side. And then what this fourth axiom says in a diagram is, of course, that when we compose these morphisms on this side and then map them, we will get exactly that composite. So F1 of G composed with F will match with F1 of G composed with F1 of F. So we've now concluded defining what a functor is. Basically, a functor is a pair of maps, is a pair of functions. If I want to write it formally out, we could say that F equals the pair F0, F1. Although we did remark that F0 is actually uniquely determined by F1. So let's write our definition. F is a functor when the conditions 1 to 4 hold. All right, so we've now given this definition of a functor, and we want to naturally look at some of examples of functors. For those of you who were attending or have listened to the lecture afterwards, you will remember that we introduced the notion of a category by abstracting from two different special cases of categories, monoids and preorders. So it would be natural to look at functors in those special cases. So our first example will be a functor between two single object categories. A single object category is essentially the same thing as a monoid, right? So if I have only one object in my category, let me actually call this object C, and the other one will be called D in the other category. So all morphisms then are morphisms that loop into C, and the morphisms in the other category, all of them also loop into D. And so the set of morphisms of the category C, C1, together with composition and together with the identity morphism, which is E of C, they constitute a monoid. And the same is true on this side. Now, we already remarked that the F0 map of the functor is uniquely determined by the F1 map. But in this case, this is even more obvious because there is only one object here. So the F0 map must map this unique object to the unique object on the other side. Hence, we can ignore its presence because it's uniquely determined. So then a functor becomes reduced to the F1 map. So it will be a function from C1 to D1. And we can now write down these four properties for the functor in this special case. The first property was commutation with the domain map. But if you look at that, so let me actually copy it from here. So I'm going to explain something that for many of you maybe you already see the triviality of what I'm going to explain, but if you do, then please be patient. So F0 of domain of F for arbitrary F. Well, the domain of arbitrary F is C, right? And F0 of C is D. That's the only object we have in the other category. And of course, that will be equal to the domain of any morphism in the other category. So it will hold trivially. So this property holds for free, just because we only have one object. In exactly the same way, the second property will hold for free. So this will be F0 of C, and that must be D, and D must be the codomain of any morphism in the other category. So this will also hold for free. The properties 3 and 4 will not hold for free. The property 3 is preservation of the identity morphism. So we will be saying that F1 of E of C equals E of D. Why did we say that? Well, we should have said it equals E of F0 of C, but remember F0 of C is D. So then it reduces to this equality that F1 of E of C equals E of D. And then preservation of composition, F1 of G composed with F must equal F1 of G composed with F1 of F. And I'm maybe should be more consistent with my own self and keep the subscripts under the composition symbol. So the axioms of a functor reduce to the properties 3 and 4. Now, keeping in mind that single object categories are nothing other than monoids, would anyone like to tell us what are these axioms in the context of a function between monoids? While you're thinking about that, let me make my screen bigger. We are preserving the entire structure of a monoid, right? And that's exactly what we're doing. We're preserving the monoid multiplication, and we're preserving the identity element. This is nothing other than a homomorphism of monoids. So we can now say that a functor between single object categories is the same as a homomorphism between the corresponding monoids. If you have any questions, please ask them. You don't have to raise your hand. You can just unmute your microphone and ask your question. If there are no questions, then I'm going to move to the next example. Our next example is a functor between preorders. Let me remind you what that is, what a preorder is. A preorder is a category where between every two objects there is always at most one morphism. So if between every two objects, I will call these objects with small letters now because we will drop the notation for arrows since it's always at most one between two objects. So if there's always at most one, then the information about morphism is fully captured whether there is one or not, right? And so this becomes a binary relation between objects. So we write that x is less or equal to y when there is such a morphism, and if there is no such morphism, then we will say x is not less or equal to y. From the previous lecture, let me remind you as well that the axioms of category reduce to this relation being reflexive and transitive. So the preorder then becomes a set P, but let's call this set C0 to be consistent with our category theory notation. C0 and this binary relation that tells me whether there is a morphism or not. What the name of the morphism is kind of becomes irrelevant, because we only care if there is one when there is only one at most. So we forget about the name, and just like here in the previous example, because there was only one object, we could forget about the name of the object and just keep track of what names the morphisms have, and that's how we get a monoid. Otherwise, we don't formally get a monoid yet until we forget about that object, right? So let's look at what will happen to the definition of a functor in the case when it runs between preorders. So this is the other extreme scenario where the information about the functor now becomes reduced to the F0 map rather than the F1 map. Why is that so? Well, let's look at the F1 map. What is F1 map supposed to do? So if my two categories are C and D, and I have a morphism here, and let us actually call it something in order that we can write out the equation defining the F1 map. So F0 map will map X to some object of D, and it will map Y to some object of D as well. And then by the axioms 1 and 2, right, it must map F to a morphism which will be called F1 of F, right? But that morphism needs to run from F0 of X to F0 of Y, right? But remember, there is only at most one such morphism there. So we don't really have much choice. The F here, when it exists, must map to the one that exists here, since there is only one such. So the F1 map becomes uniquely determined then, right? There is no choice for what F1 of F should be. It must always be the unique one we've got. If we've got one. If we haven't got one, then we won't be able to establish a functor at all. So that's how F1 gets dropped. And the entire information about the functor then becomes encoded by the F0 map. But we shouldn't forget that F1 must exist, right? And so our first axiom on F0 will be that if X is less or equal to Y in the preorder C, let me insert the subscripts here as well, like I did before, then F0 of X must be less or equal to F0 of Y in the preorder D, in the category D. And this condition is the one ensuring that F1 exists. So it's not one of the four conditions here. We haven't yet fully explored. I mean, it's kind of mixture of these two axioms together with the presence of F1, right? So this ensures F1 is defined. As well as 1 and 2 hold. And not just that it ensures that, it's equivalent to that. So let's write it that way then. This is equivalent to F1 being defined as well as 1 and 2 holding. So then it remains to look at axioms 3 and 4. Let's copy paste these axioms and see what they translate to in the case of a preorder. Okay, so this morphism here is what? I have an object. Okay, let me first replace capital letters with small letters because we decided to write the objects in the preorder by small letters. So this will be x, and this will be x as well. So if I have an object x, E of x is that identity arrow of x, which is just there to remind me that x is actually less or equal to x. That's coming out from the reflexivity rule, right? Now, f1 of that, because f1 must preserve domain and codomain, f1 of that will be a looping arrow from f0 x to itself, right? So this is f1 of e c of x. What about this? f0 of x is this object here, and this is the identity arrow of that. So the identity arrow of f0 of x. And the condition requires that they're equal, but now I claim that they will be equal for free. Would you like to tell me why?
Because the identity arrows are always equal, they are unique.
But how do we know that this one is identity arrow?
Because there is at most one arrow between objects in the category.
That's right. Yes, yes. Thank you, Mick. That's right. And also, Soshan wrote the same thing on chat. Thank you very much. So just as before, there is always at most one arrow between an object and another object, and so there must be at most one looping arrow. And now we've got two candidates, therefore they must be the same. So in other words, this axiom holds for free. Now let's look at the composition axiom. The composition axiom says that if I have arrows arranged this way, f and g, and I compose them, but remember there is only one way of composing them, that is exhibited by the transitivity law. If x is less or equal to y and y is less or equal to z, that forces x to be less or equal to z by transitivity. It's one of the axioms of a preorder. And now when we take f of f, f1 of f, which will now be arrow from f0 of x to f0 of y, and then f1 of g, which is an arrow from f0 of y to f0 of z. If we compose them here, this will be an arrow from f0 of x to f0 of z. But if we try to apply f1 to this, that will also be an arrow from there to there, again by the fact that the functor preserves domains and codomains. And once again, we have a situation where we have two arrows from the same object to the same other object, and therefore they must be equal because we said there is at most one arrow. So this will be equal to that. And so we get that the second axiom also holds for free. So it's quite remarkable that in the case of preorders, the entire complex concept of a functor reduces to something very simple. It just reduces to a monotone map, right? A map that preserves the order. So this becomes then the axiom that defines the functor. So let's write this out. A functor between preorders is an order preserving map. Between them. Okay, so categories have dual nature. On one hand, they are mathematical structures just like any. And in that sense, it's very often useful to think of them as kind of merger of the notions of monoid and preorder. And so that's why we've exhibited the notion of a functor in these two examples. But they also have another nature. They're also at the same time something that describes the structure of a universe of mathematical structures of the same time. Okay? And so let's look at examples of functors in that realm. When our categories C and D are universes of other mathematical structures. Among the examples of categories of that kind, of where category becomes a universe of mathematical structures, among such examples, we looked at the category of sets last time, and as well as the category of vector spaces. Let us look at these two categories now as examples, and let's try to think of some examples of functors between these categories. So our first category is set, and the other category is vec, or vector spaces, or a field F, and if you prefer, the field can be the field of complex numbers or the field of real numbers, or maybe Z2, whichever your favorite field is. So remember that functor needs to have two kinds of mappings: mapping objects and mapping morphisms. Usually, when we are dealing with worlds of mathematical structures, we usually first start thinking in terms of what to do with objects, and then see if what to do with morphisms emerges naturally from what we decided to do with objects. So if I have a set X, is there natural way of producing a vector space out of it? Any ideas? Let's make this story a little bit simpler, not to have to use too much of advanced linear algebra. Okay, we've got one answer here in the chat. There is a keyword mentioned there. We can get basis, so that's a good idea. It sounds like a very good idea. So let's turn that keyword into a functor. So f0 of x, I want to define it in a certain way. Would anyone like to tell me explicitly, after the hint that Ephraim gave, what we should do here?
You think we must get F0 as a vector space, no?
Yes.
So we can take all the elements in X and the kind of linear combinations.
Yes. So we will create a vector space where X is the basis.
Yeah. So we take the elements of X and their linear combination, all the linear combinations.
That's right. So this will be is a vector space with basis X. And there is a theorem in linear algebra that says that for every set, a vector space with basis that set exists. Okay, now let's see what we can do with morphisms. So this will be our F0 map. So if I now have another set and I've defined another vector space, with basis y, what would I do with a function? A function from x to y is a morphism in the category of sets. In the category of vector spaces, a morphism is a linear map. Now, as Charles remarked, elements of this vector space are finite linear combinations of vectors from the set X. Maybe that will give us an idea how to define a linear map, which will be the F1 of F. So I need to first of all define this map. So I need to say what will happen if I apply this map to a linear combination. Let's say maybe I want to call my field R, so that I can use small r here for the linear combination. So first I need to define this map, and then I need to make sure it's a linear map, right? Any ideas how to define a map from F0 to F0 of X, sorry, to F0 of Y, based on a function f that maps the basis vectors of one vector space to the basis vectors of another vector space?
Maybe I should come in there. I'm trying to hold off since this is I'm a functional analyst, and this happens all the time in functional analysis. The linear map is uniquely determined by what happens to the basis vectors. So what will we do? We will take the coefficients out, R1, F1, F, x1, that will be what the function should do to the first basis element, etc. Oh yeah, like so.
That's right, yeah. And by the way, the fact that the linear map is uniquely determined by what happens to the basis vectors, we will later on see how this fact becomes a consequence of a general phenomenon dealing with certain kind of functor building categories. But yeah, so this is how we define F1 of F, and for those who are experienced with linear algebra, you will already know or guess that this map must be linear. Basically, we're kind of forcing it to be linear in some sense, because being linear means that it preserves linear combinations. So we've now defined both maps, F0 and F1, and we need to make sure that all these conditions hold, 1, 2, 3, 4. The first two conditions was about the matching of the domains and codomains, and that's basically by construction they match. From this picture, it's clear that the preservation of domain and codomain takes place. So we just need to check preservation of composition and identity maps. Identity map here is the identity function. And if I expand this formula, if I compute this formula, simplify this formula rather, for the identity map, I will of course get that the value of F1 of identity at this linear combination is R1 of the identity map applied to each of the basis vectors. And of course, the identity map maps everything to itself, so it's just this. So you see that this is in fact nothing other than the identity map of F0 of X applied to the same linear combination. Since the linear combination didn't change, it remained exactly the same vector. So identity maps are preserved. That's good. And the last thing now to check is that composition is preserved. So for that, the diagram would be that we have F, and it's very useful to draw these diagrams when you want to check such things. So working in category theory brings in kind of geometric dimension to algebraic computations. So we've got the setup, and we now want to compose the maps here and then map them, and sorry, map the composite, and that needs to equal to the composite of those two maps. And so let's perform the computation. So if I take F1 G composed with F, and I apply that to the linear combination, this will equal, by definition of the map, it will equal R1 of G of, okay, maybe I should first write G composed with F of X1 plus all the way up to Rn times G composed with F of Xn. And then I can I can do something which is also very standard technique in mathematics. We try to separate this, right? So this is the same as G applied to F applied to X1. And then we start taking the G and the F out one by one. So we first take the G out. It goes out by the definition of, no, sorry, something is wrong here. No, nothing is wrong, sorry. So this is actually, by definition of F1G linear map, this is actually equal to that map applied to R1 F of X1 plus all the way up to Rn F of Xn. And then we take the F out, and we just think about this one, this expression here, and that is the same as F1 of F, that linear map applied to our linear combination. And I just need a bit more space here. So that, of course, can now be rewritten as, so we now put these two maps together. This is the composite of F1G with F1F applied to the linear combination. And that's what we wanted, actually, because we wanted to prove that these two are equal. Remember, we wanted to prove that if I compose first and then apply the functor, it's the same as applying the functor first and then composing. So I wanted to prove this is equal to that. Now, to prove that two linear maps are equal, I just need to make sure that they act the same way on vectors. So I took a random vector in the domain of my composite, and then I applied that linear map to it, and I saw that it's the same as applying the composite to the same vector. And this is true for every vector, therefore the two maps are equal. Okay, so we get a functor. We get a functor from the category of sets to the category of vector spaces. Let's call this functor F. Now you see that it may take a while to build a functor. It takes some computations and so on, but once you become fluent in category theory, then these kinds of computations kind of happen in your head in a matter of a second or so, and so you don't really write all these things out. You just say that you just define the F0 and the F1 map, and then sometimes you don't even define F1 map. It's so obvious how to define it, even though there could be many ways, but there will always be, often will be one obvious way to define it, and then you just say that we have a functor, and you don't need to check the details unless these details are really non-trivial details, then you do want to check, of course. We have a question here in the chat. What is the purpose of the line that replaces the composition symbols with brackets? Are we saying that composition in the category is the same as composition of functions in set? Yes, it is. This is how we defined composition in the category of sets. So in the category of sets, composition of morphisms was defined in terms of composing functions. So this composite morphism applied to an element x is by definition equal to g of f of x. Does that answer the question?
Yes, thank you.
Wonderful, thanks. Let's maybe write this as a remark here. By definition of composition in the category of sets. And the same goes for the definition of composition in the category of vector spaces. I didn't expand on these because we did discuss how compositions are defined in these categories in the first lecture. Okay, now that after a lot of effort, we finally have a functor going from sets to vector spaces, there is a natural question that arises, which is whether we have a functor going backwards. And so let's try to build one. What about going backwards? And perhaps we'll be a bit less detailed in our formal establishment of the functor in this direction, because it will be even more obvious that the thing we will point out will be a functor. I'm going to call this functor u. And what would be the most obvious functor from the category of vector spaces to the category of sets? Would anyone like to give it a try? So let's just think in terms of defining it on objects. So we have a vector space. How can we create a set out of it? We could take the dimension of the vector space and the set of that cardinality that basically corresponds to taking a basis of the vector space, so kind of trying to reverse the process. But we will run into trouble because if we take the basis of our vector space as our set, then our linear map might not map the basis vectors to basis vectors, right? So we might not be able to define the function between the corresponding sets. Let's maybe it's worth expanding on that. So if this is a basis of V, right? And then we have a linear map F between V and W. So U of W will be some basis of W. We would now want to have something natural here, a function between those bases, and we would probably want to hope that we can restrict f to basis. So it will be just restriction of the function f, but the problem is that when we restrict this to the basis, the values on basis vectors might not necessarily be inside the basis we selected here, right? So that doesn't work. And there was another suggestion which was to map the vector space into the set of all vectors of the vector space. So this will be the set of vectors in V. Now keep in mind that this is not the same thing as V itself, because V has a structure of a vector space. It's not just a set. It has a binary operation of addition of vectors, which could be chosen in many different ways, but one specific way has been fixed. for a vector space. It has an ability to multiply scalars with vectors. So there's a whole lot of structure that comes with V. And with this functor that we're trying to build here, we will erase all of that structure and just leave the raw set of vectors. Okay. We can think of this as the underlying set. That's why it's called U. So the underlying set of V. And of course, by the way, linear maps are defined. What is a linear map? A linear map is a function between underlying sets, which is linear, right? So obviously we will have the same f now acting as the U functor applied to f. And the fact that it preserves compositional identity morphism is not very obvious, because composition of linear maps was defined as composition of these functions. So if I compose them here, if I compose morphisms, linear maps here, right, that is the usual functional composition, which happens to be linear map. And so because U of G is defined as G, then of course U of any linear map is defined as that same linear map seen just as a function between underlying sets. So then this will automatically equal that which is U of G composed with U of F. And in the same way, U of the identity map in the category of vector spaces is just the identity function, which happens to be a linear map. So then it, by our formula for U, it must be equal to the identity of V, which is of course identity of U of V, where now I write the same V for the vector space and the underlying set. So here that V represents the underlying set. Maybe I should just write it this way to make it a bit more clear. So we get a functor backwards. So okay, so the second round it wasn't so complicated to build a functor. Maybe this means that we're getting good at this, and let's try to build more functors. If you would like to propose a functor, please go ahead. Otherwise, I will wait first for what you propose, and then I'll wait some ideas to emerge in my mind.
I have an idea. It might be wrong. So tell me if it's wrong. Can we map, let's say, the category of vec into set, but we send everything to the empty set and to the empty function? That it feels to me like that should be a legitimate functor. And in that vein, it also feels to me that that works generally, that we can send any category into set just by doing the trivial thing and sending everything to the empty set and to the empty map. It's a bit of a naughty or useless functor, but it feels to me like that is a legitimate functor.
So thank you very much, Mick. I would like to propose a vast generalization of your idea. We have arbitrary two categories. We pick a random object here, call it D. And we send, so this D is a fixed object, maybe I'll call it D0. Oh no, D0 is not good because we use 0 for a set of objects. So let's just fix an object D. Let me denote it like this in a fancy way. And then we map every object of C to that fixed object D. And we map every morphism. Yeah.
To the identity morphism?
Yeah.
Ah, okay.
And we map everything to the so it's a kind of an analog of the constant function between sets, right? We can call it a constant functor. So we map everything all the objects we map to the same object D, and all the morphisms we map to the same morphism identity of D. Why is it a functor? Well, preservation of domains and codomains is obvious from the picture I drew, whereas preservation of identity morphisms is also obvious because everything is mapped to the identity of D, and D is the value of F at an object. So this is another way to write what we previously wrote as F of F. So this was supposed to be F1, right? And this is supposed to be F0. But usually, I didn't tell you this before, but usually we drop the subscript 0 and F, and we just call both of these, we just write F as a function that applies to morphisms as well as a function that applies to objects. But for the time being, let me stick to the more formal notation I introduced before. So we've seen this equality in the form of F1 of E of C being equal to, so this happening in category C, being equal to E D of F0 of C. So this holds because everything was mapped to identity object morphism, and then composition also becomes trivially true. So G composed with F will be equal to identity of D by definition of F, but of course identity of D is equal to identity of D composed with identity of D, and we can now interpret identity of D in two different ways, one as F1 of G and the other as F1 of F. So we indeed get a functor. So this functor F maps all objects. So while I'm writing this out, please go ahead and think of other examples which we could consider. F maps all objects to a fixed object D and all morphisms to identity of D. Let us have one more example, and then we conclude with the examples and maybe try to establish some properties of functors. So remember, we want to think of, in the second set of examples, we want to think of categories as universes of structures. So if there is a construction that allows you to construct one structure out of another one, this is the kind of thing you want to test to be a functor or not. So in your interest of mathematics, the structures that you're considering there, maybe there is a construction that you begin with a certain structure of one kind, and then you do something to it, and you get a structure of another kind. And these kind of things usually end up being functors. So let's try to think of some example in that spirit. I mean, this was a very good illustration of that idea, right? We began with structures of one kind being sets, and then we build a vector space out of it. And in the other direction, we began with a vector space, and we created a set out of it, which wasn't big deal, of course, but it's still transferring from one universe of structures to another. What about the category of matrices that we looked at in the previous lecture? Matrices over, let's say, a field R. And let's go from there to the category of vector spaces. over the same field R. Let me remind you that in the category of matrices, objects were natural numbers, and a morphism was a matrix. So morphism from N to M was an M by N matrix. So its entries would be A11 up to A1N, and then in the last row we'll have AM1 up to AMN. And another morphism, B from M to K, will be a K by M matrix. So we will have B11 up to B1M. And in the last row, we'll have BK1 up to BKM. Composition of morphisms was defined as matrix multiplication. So B composed with A is just the usual way we multiply matrices. I'm not going to write out that formula because I think it's familiar for everyone. Where can we map a natural number? It must be mapped to a vector space, and then the matrix would have to be mapped to a linear map. This is, of course, something very familiar for everyone. And it is very familiar, and it might be kind of, you might think it's maybe similar to this functor, but actually it won't be similar. Why will not it be similar? Because here, the linear maps we got on this side were very special ones. They were the ones which map basis vectors into basis vectors, but not all linear maps are like that. Remember, that's why we're not able to go backwards. With this functor, the situation will be different. So we map n to the vector space, which is an n-dimensional vector space. So R to the power n. That goes for every natural number. And now we must specify the linear maps. But these vector spaces have a standard basis. Basis consisting of vectors where one of the coordinates is 1 and all the other coordinates are 0. And then we know from linear algebra that a matrix defines a linear map from Rn to Rm. So our functor f is defined this way on objects. And on morphisms, it's the same matrix A seen as a linear map. And this linear map, maybe I will keep it a bit more formal and just put back the subscripts and so expand what this does. So this is a linear map that maps a vector in Rn, and the vector in Rn can be seen as a column of its coordinates. So let's say v1 up to vn, and we define that to be A times that column. A is an m by n matrix, so when I multiply A by that, we will get a column of height m, precisely something that fits as an element here. Okay. Now, why is f functor preserving composition? Well, because f1 of B composed with A. Let's investigate what it will do to a column vector. It will multiply B composed with A as a matrix. It will multiply with that column. But remember what composition is. Composition of matrices is just multiplication of matrices. So we get this. And we know that multiplication of matrices is associative. So if we have brackets here, we can rearrange these brackets. So we can put brackets this way. And then, of course, A times that thing is nothing other than f1 of a of that vector, right? So we'll have b times f1 of a of that vector. But b times a vector is nothing other than f1 of b of that vector. And now these are linear maps, and if I apply one linear to another and then finally apply it to a vector, it's the same as applying the composite of these linear maps to this vector. So as a result, what do we get? We get something that cannot fit on my screen anymore, so let me make it a bit smaller. As a result, we get that, you see, this linear map applies the same way to an arbitrary vector as the other one. So the two linear maps are equal. So we get that f1 be composed with a equals f1b composed with f1a. And of course, we already know this from linear algebra, because when we represent linear maps as matrices, we know that matrix multiplication corresponds to composition of those linear maps. So we didn't really establish anything new here. And in the same way, we know that the identity matrix is the identity linear map. And so we get this nice functor from the category of matrices to the category of vector spaces, where, unlike in the other example, all linear maps can be captured to be coming from the left side. And moreover, this functor is kind of injective. Both f0 and f1 maps will be injective. And later on, we will see that there is something much more interesting going on here than just a single functor. Especially if we restrict on this side to finite dimensional vector spaces, we will get that this functor is something that will be called an equivalence of categories. And that basically one of the category theoretic ways to conceptualize the important phenomenon in linear algebra, that linear maps can be represented using matrices in a way that matrix multiplication corresponds to composition of linear maps. Any questions on this example?
I have a small question on terminology. Is it? I assume there is a good reason why we're avoiding the word isomorphism of categories. If we restrict, for example, in this example, matrices in finite dimensional vector spaces, why would we not call it an isomorphism of categories?
We will not call it an isomorphism of categories for the simple reason that it will not be an isomorphism. And it will not be an isomorphism because for each dimension we have multiple vector spaces having the same dimension. But all of them are isomorphic. And so when you have an isomorphism of structures, you want to have one-to-one correspondence, right? So here we don't quite have one-to-one correspondence. We have this duplication of yeah. But the duplication is such that pairwise they're all isomorphic to each other inside the category. So, and that's what defines an equivalence of categories.
It's kind of a quotient map. So in the matrices, so in Vec we regard, for example, all we regard R3 and the vector space of second-degree polynomials as different vector spaces.
Yeah.
Okay, understood.
And if we don't want to, if we want to regard them as the same thing, then we basically reduce our category to matrices, to the category of matrices.
Yeah, so the category of matrices is kind of like a quotient of Vec, where we kind of quotient at the.
Yes.
Okay, thank you.
Yes. But it's also a nice quotient in the sense that those objects that have been stuck together, they were isomorphic objects inside the category. Okay, so then let us now move to establishing some very basic facts about functors. this might be a bit kind of extra dimensional thinking now, because in what follows in the next few minutes, we want to think of categories as just a single object. So, I mean, it could be difficult to imagine that, because a category itself is a universe of structures, and each structure itself has some objects in them, which themselves might be some complex entities. So it's almost like flying up far enough that the entire city now just becomes a single dot. Okay, and maybe even an entire planet becomes just a single dot, which is not maybe so difficult to imagine, because when we look at the sky, the stars are just dots for us. So if I have two functors and three categories, C, D, and E, and the functors, let's call them F and G. So let's say here that we are now back to general functors. I can compose functors. Well, remember, functor is a pair of maps: F0, F1, G0, G1. I could try to define the composite of functors to be just by composing each coordinate. So to be the composites of those coordinates. But how do we know this is still a functor? We have to check that it's still a functor, and we will check that with diagrammatic arguments. I'm also slowly trying to get you used to working with diagrammatic arguments in category theory. We will use a bit of equations as well. So f being a functor can be represented by the following picture. So we've got, whenever we have two morphisms, f and g, right? When we apply the functor f, we get this setup, and already this picture shows to me that the functor must preserve domains and codomains of morphisms. And to indicate that it must also preserve composition, I'm going to also draw a composite here. And I'm going to map that composite here, which will then be f of g composed with f. But I'm not going to draw another thing which is meant to be the composite of these two, because that thing is meant to equal to this. Okay. And maybe I also want to keep the information that the functor must map identity morphisms to identity morphisms. So here we have the identity morphism of f of y. And I'm being a bit inconsistent here with myself, because here I've maybe I should be a bit more consistent. Maybe instead of this, I should write f of g composed with f of f. But I keep in my mind that the fact that this actually must be f applied to that composite, because f must preserve composition. Then, with this explanation, this picture is kind of illustration of what it means for f to be a functor. And let's draw a similar illustration of what it means g to be a functor. But now let's apply that illustration to this starting scenario, where we're applying g to a setup that's already looks like this. And so then we'll have here on this side, we'll have g of f of x. And remember that these must have subscripts, 0 and 1, depending whether we're applying to object or morphism. But for now, let's start dropping those subscripts. So g of f of x, since we distinguish between objects and morphisms by notation, by using capital or small letters, it's not going to cause confusion if we drop the subscripts there. So g of f of x, which is meant to say g0 of f0 of x. Okay, that's g applied to this object. And then we have g of f of y and g of f of z. And here we'll have g of f and g of f of g. And so because g is a functor, we have a similar picture here where we write here the g of f composed with g of f of g. And actually, it's the other way around. My apologies. So this is g of f of g composed with g of f of f. And here we have the identity arrow of that g of f of y. And we kind of agree with each other. We see it from the picture that the fact that g is a functor, in particular, in the case when our starting point is represented by this picture. So this picture represents that f is a functor. This picture is a specialization of the fact that g is a functor. But now if I combine the pictures together, right? And if I look at this picture together with that, and I kind of take off the middle part, then I will get a picture that tells me that g composed with f is a functor. Okay? All right. Now let's write all of this out algebraically so that we are sure that we're not making any hocus pocus here. So a preservation of domain and codomain is fairly obvious, but let me still write it out. So g of f of domain of a morphism f, so the domain is taking place in the category C, and then this will be f0 and g0 that will be applied to it, right? Because f is a functor, well, first of all, the composite, so if I want to be very formal here, I first need to write the composite of g and f, and then take it 0, right? Let me go back to my notation here. So remember, the composite of g and f is defined as this pair. So, but when I have a functor h, if this was called h, right, this would be h0 and this will be h1. So that means that my g composed with f0 is equal to that composite of those g0 and f0. In the same way here, g composed with f1 equals to g1 composed with f1. So I want to prove that gf is a functor. So then I have to, one of the things I have to check is that g composed with f0 applied to the domain of morphism will be whatever it should be, and then let's do the computation. So g composed with f0 is defined as g0 composed with f0. Now that has to be applied to d of f. And by definition of compositional functions, this is just g0 applied to f0 applied to d of f. And by definition, by the fact that f is a functor, so we're basically using this picture here now. By the fact that f is a functor, this will be a domain map in the category D for f1 of f. And by the fact that g is a functor, so using this picture, but we're not really using a picture anymore, we're just reducing it to computation. So this will be domain map in the category E of g1 of f1 of f. And this will be, of course, this is the same as g1 composed with f1 applied to f. And then this is the same as g composed with f1 of f. And that establishes the, let me see which number it is. So it's the first property, this property, no, not that one, sorry. This is not the first property. It is this property of the functor. And similar computations can be used to establish other properties. I'm not going to do that because it will be very boring to watch that happen. It's better for you to check these computations yourself by hand. It will be very straightforward computations. So other axioms. So other axioms meaning 2, 2, 4 for a functor can be verified similarly to hold for G composed with F if you do not believe the picture. So yes, we do use pictures for category theory, but every time we use a picture, it is extremely straightforward to turn this pictorial argument into an algebraic computation. Okay. So functors compose. Composite of two functors is a functor. Moreover, there is something called identity functor. So I think you might now see where I'm trying to go. Functors compose, and there is an identity functor for every category. So what is the identity functor? Identity functor is defined by the pair identity function over the collection of objects and identity function over the collection of arrows. So it maps every object to itself, it maps every arrow to itself, and it should be fairly obvious that this thing will be a functor. It is easy to see that this is a functor. Now we have something interesting happening, right? So we have the world of categories, right? And remember, each category is a universe of mathematical structures of a given time. And then we have these functors between them, which are basically ways of transporting structures, turning structures from one type to another type. And they can be composed. And we've got identity functors for every category. And in fact, it's not difficult to check that we have the following laws for composition of functors. So if I have 4 categories and 3 functors, F, G, and H. Remember, composition of functor is just composing the object maps and the function maps. So it shouldn't be difficult to see that if I happen to compose H with G and then compose that with F, we will get the same functor as if I first compose G with F, then compose that with H. So that's one rule that holds, that these two composites are equal. In other words, composition of functors is associative. So we're claiming that this will be equality. And the other rule that holds is that if I take the identity functor, which is a looping arrow into C, and I try to compose it with the functor E going into my object, I will get back the same functor E. And also, if I compose it with a functor going out of the object, I will get back that same functor. So what does this mean? What conclusion does this bring us to? The fact that functors between categories compose in an associative way, and there are identity functors for every category that satisfy these identity laws. What do we get as a result? So we get that categories and functors with composition of functors defined above itself forms what? Have I lost all of you?
Gregor gave an answer in the chat. I was holding off a bit.
Right, thank you. Yeah, sorry, I didn't notice that. Yes, we get that. We get a category, but we have to be careful now. There is certain problems we will encounter if we just call this thing a category. The problem we encounter is the problem of size. Now, this idea that by collecting objects together gives you an object which is of the same type as the type of objects you collected, right? This idea we have already seen in set theory. So by collecting all sets together, we get a collection of sets which itself is a set, right? But actually, it's not a set. So let's talk about the problem of size. So let's say, so let me first remind you of the problem of size in the world of sets. Let's say this is the bag that contains all sets in it. The bag of all sets. This bag itself looks very much like a set, right? So we can think of sets as dots, okay? And this is the bag of those dots that we call sets. And this bag itself looks like a set. So we have another dot, which represents the bag. And the problem of size tells us that although it looks very much like a set of its own, we must not necessarily assume that this dot is one of the dots we started with, okay? So we do get a set, but it will be a set of, it will be a set that does not live among the sets that we started with, okay? And this is the famous Russell's paradox that demonstrates that you can't just have any bag of sets defining a set itself. And then the whole axioms of set theory is about choosing which bags of sets are actually sets and which are not. I mean, not which are not, but which definitely are. Not all of them can be by Russell's paradox. So this is the collection of all sets, which looks like a set, but it need not be. Now, when we defined a category, right, we said that the objects of the category form a collection. We didn't say it forms a set. The reason why we didn't say it forms a set is because we wanted to consider the category of sets where the collection of objects is the collection of all sets. And just by this remark, this collection of all sets is itself not a set. So our definition of a category already was kind of stepping out from traditional boundaries of Zermelo-Fraenkel set theory. So once again, this is the bag of all sets. The more elegant name for this is a universe of all sets. So the bag of sets. And our collections of objects for a category were not necessarily sets. So there were things of this kind which which are collections of sets, but themselves they might be lying outside. I mean, some of them might be lying inside, but some of them might be lying outside of the realm of the bag of sets. So let me draw some of these here. And so on. So as a result, we get the next layer, which is the bag of collections of sets. Sometimes they're called classes, but the term class is more specific to set theory, where we define exactly how we are able to describe a class, and it must be in terms of a first order formula. The bag of collections of sets. Now, remember that categories live in this world. The way we define categories live in this world. This is where categories live as objects. So if we now take all possible categories, this will be going one layer higher. So the collection of all categories. Okay, maybe I shouldn't have encompassed the entire area, because there are other things apart from categories here. So the collection of all categories is something that is of the next level. So this is the collection of all categories. The collection of all functors, again, will be something of that layer. So we will get, we do get a category as we described earlier, but we get a category which now lives not in the usual layer where we define the categories to live, but in the layer right after that. We call such a thing a large category. In fact, the way we define categories, I mean, terminology differs based on literature. So, and usually authors kind of fix terminology for their own usage. So we define categories the way we define them. So they already, the way we define categories, they already live outside the usual Zermelo-Fraenkel layer. But now, if we want to take the category of those categories, then that category will be living in a layer one above, and we will call such a thing a large category when it lives at layer one above. So I'm going to insert here the word large. Now, all of this might be very new to you if you haven't thought very carefully about axiomatics for set theory. I will be happy to engage with discussions with you about this topic. We will not be able to include such discussions in this course because it's a course of its own in a sense. But I hope that at least some intuition was provided here in terms of the size problem. Any questions?
I have a rather naive question. I assume that there will then be an analog of Russell's paradox, but for categories.
Yeah, so I mean, we don't really need an analog because already you can think of a set as a category where there are no morphisms apart from identity morphisms. So sets automatically are categories in a default way like this. And so one can just use the same Russell's paradox. Just think of sets as a category with identity morphisms being the only morphisms.
Okay, and just viewing it through that lens. Okay.
Yeah.
Thank you.
That is another example of a category which we haven't discussed. So we said that we can view monoids and preorders as categories, but we also view sets as categories by just introducing the identity morphism and nothing else. This will be called discrete categories.
Yeah, Zurab,
Yes?
yeah, just a clarification point. In this case, by talking about large categories there, by implication, it implies that the categories we're talking about, we can refer them as small categories.
No. So small categories will be those that live in here. So they will be those for which C0 and C1 themselves are sets, not just collections of sets.
Okay.
So we have three layers. We have large, so this is the large category layer. This is the usual categories layer. And this is the layer of small categories. And in our examples, the category of matrices is a small category because the set of objects and the set of morphisms there are just sets. But the category of sets is not a small category, it's a category. And this is what I said, that terminology slightly might differ from author to author. So I wouldn't be surprised if someone calls what we call categories, they call them large categories. And then this will be called super large or something like that. So I would like to conclude with just a glimpse of what could come next. It turns out that when we go to this higher level, so in the beginning we started off with sets. I mean, we didn't start off with sets, but one can say that foundations of mathematics through set theory, which was the first formal foundations for all of mathematics, begins with sets, right? And then when we moved from sets to categories, and in fact there is a way to give a foundation of mathematics using category theory. So what happened is that now sets, so the objects obtained morphisms between them. So you can think of it as kind of complexifying the starting data, where we no longer start with just a set of objects. We start with a more complex situation where we have objects and morphisms between them. But then these kinds of things, so just like sets form a category, right? Which is the category of sets. And when we move from sets to categories, the objects obtain these arrows between them. Now, categories form a category as well. More precisely, large category. And just like in the previous case, we are expecting these things to have more complex information than these ones did. So a category has more complex information than individual sets do. A category is not just a set of objects, also arrows between them. And in the same way, we expect that this large category we get will have more complexity to it than the original categories did. But now, how can we complexify it even further? And there is a certain kind of similarity into how the complexity enters. So you can think of objects as kind of zero-dimensional morphisms, and you can think of morphisms as like one-dimensional morphisms. And then you will have two-dimensional morphisms, which will be morphisms between morphisms. So here we had objects, then we introduced morphisms between them, and now we're introducing morphisms between the morphisms. This will be called a two-category. such a structure, which allows morphisms between morphisms. We're not going to go into two categories in our course, but we are going to explain how we can introduce the idea of a morphism between functors. So if I have two functors going in the same direction, there will be a very natural notion of a morphism between functors. And it will be called a natural transformation. A natural notion of a morphism between functors arises, called a natural transformation. And in fact, right at the beginning, when Samuel Ellenberg and Saunders MacLean were inventing category theory, it all started with natural transformations. They identified, so MacLean came from algebraic background, Ellenberg came from background of topology. There is actually a nice paper by MacLean which explains how they got started to working on category theory. And so early on in their work, they identified a certain interesting phenomenon that they called natural transformation. It was some kind of transformation which seemed to be very natural. And they wanted to formalize that. They wanted to formalize the idea of a natural transformation that they picked up by trying to merge their works from topology and algebra. But to formalize that notion, they had to formalize what a functor was. And then to formalize what a functor is, they first had to formalize what a category was. And that's how they arrived to categories. So in fact, in a sense, this is going to be the main player. But then there is a lot of category theory which develops even without natural transformations. But natural transformations are certainly not less fundamental than functors in category theory. And that's what's coming next. So at the next lecture, we are going to look at natural transformations. We will see why they are so natural, and we will look at their examples and give a precise definition, of course. And then once we've done that, then we will be able to do lots of fun with category theory, even more fun than we had so far. Any final remarks or questions before I stop the recording?
Yes, I have a question.
Please.
So you said we call these categories two categories. So I wonder now whether we could refer to sets as zero categories and
Yes.
the other categories as one categories.
Yes.
And whether there are also whether there's also such a thing as three categories. With
Yes, there are.
Okay.
There are n categories, and as the dimension goes up and up, there are different ways of defining these things. So there are different notions of n categories for a higher n. And higher category theory is a branch of category theory that studies these notions and their applications. And one of the big challenges in higher category theory is finding a good definition of a higher dimensional category theory.
Okay. Oh, that's very interesting. Thank you very much.
You're welcome. Any other questions? Yes, good morning.
The idea of identity functor, we could also then look at a category then as a sort of monoid. If we look at the identity functor in the sense of, for instance, an identity permutation, and then we could look at functors on the same category as what's this? Yeah. So we look at permutations as if though they're functors on the same category. Yes.
Yes, very true. We could consider the monoid of n the functors of the category, where the identity functor will be the identity element. It's true, yes. And in fact, because of natural transformations, these monoid of n functors will actually turn into a category of its own, where morphisms are the natural transformations. But that will come next.
Yeah, if I could come in there, that means that you, if you look at the category as a monoid, then it goes one level higher. You have to go one level higher, otherwise.
Exactly. Yeah.
Okay.
And one level higher will be exactly a category. So this monoid will actually turn to a many-object category.
Yeah, Zurab, can you go back to that sketch on where it starts from sets? Yeah. When you talk about, I'm just finding it very interesting that when you just talk about the two categories, starting from sets, if you look at the sets and they look at the elements as kind of objects, it's like you are looking at points.
Yeah.
Then when you go to objects now and the arrows between objects, it's like we're looking at lines or line segments.
Yes.
In one dimension, you say you are in 0 dimension. Then when you go lifting up to the two categories, it's like basically we're passing from the one-dimensional entity to a two-dimensional entity.
Yes. Thank you very much, Charles.
I find it interesting to highlight, yeah.
Yeah, what you highlighted now actually is a very important idea. So we can take a topological space and turn it into a set by looking at its set of points, turn it into a category by looking at arrows being continuous paths from one point to another, but we identify two paths when they can be continuously deformed from one to another, okay? So that will be the arrow. So we can turn a topological space into a category, but we can also turn it into a two category where arrows are these equivalence classes of paths, and morphisms are basically these continuous mappings of a rectangle where the top edge of the rectangle gets mapped to one path, the bottom edge of the rectangle gets mapped to the other path, and the other edge is constantly mapped to the points. So this maps to x and that maps to y. And again, we would want to take equivalence classes of such things to get a proper two category. But of course, we could go higher up. We could take now continuous mappings of cubes as a morphism between morphisms of morphisms, and so this way, this is how a topological space can give rise to higher dimensional categories. And in that sense, remember I told you that categories have double nature. One is that categories themselves are structures. The other is that categories encode universes of structures. So what we're discussing now, the link with topological spaces, that's seeing categories themselves as structures. We now start to see that a topological space as a single structure can be viewed as a slightly more general kind of structure, which is, let's say, an n-dimensional category. But thanks for that remark.
I have a small question on this. So these kinds of homotopies, they form a two category, but is it in some sense a synthetic two category, because we don't have the problem of size since everything is sets? So
yeah, so that will be a small
kind of
category.
a synthetic. Okay.
That will be
a small two category. Okay,
that's
understood.
right. Yeah.
Okay.
Yeah, Zurab, another comment. It's actually very interesting to, I'm just like reflecting to it now, how do you see all these kind of, whether we can call them super abstract concepts being embedded in a kind of, even school mathematics going upwards.
Yeah. Yeah.
You see the points, the line segments, the triangles, and all these things going up. You actually, if you now look at, we have come out of a category theory, then you actually see these things right from the bottom there at, at the entry point. Yeah, it's quite interesting that. That's what I comment. Yeah.
Thank you. All right, so thank you everyone for your contributions for this lecture. If there are no further questions or comments, I will stop recording. We can still continue discussion afterwards, but if you would like to make a remark or ask a question to be part of the end of the lecture, then please do so now. Otherwise, I'm going to stop the recording.